Start.
Yeah, so go ahead and start.
Perfect. Thank you so much. Okay, so welcome to Chasing Rabbits, building a lifetime curiosity and fascination for mathematics through adventures in arithmetic. And so my whole teaching sort of career has gone full circle because I've actually gotten back to arithmetic, even though, as was mentioned as an introduction, I was a math and physics teacher for 19 years, which of course means high school. So I fell down some rabbit holes and I eventually came to the idea of arithmetic. And where I want to start is with zero. If you look up the definition of zero, I think in Oxford edition, the latest Oxford edition dictionary, you're going to have multiple meanings for it. But quite ironically and regrettably, you're not going to see any references to the Sanskrit definition of shunya, which represents this idea of nirvana. And also Brahmagupta, who was basically the founder of the idea of the arithmetic ideas of zero, his 7th century definition of zero. His definition of zero was based on addition. And there's a whole backstory here about a really poor translation of from the east to the west and east to the Middle East in terms of even Al-Khwarizmi's, what he took from zero, just meaning basically a placeholder. And it had far more meaning than just being a placeholder. And the person who I really want to credit here for guiding me in my own journey is Jonathan Crabtree. He's an Australian who spends much of his time in India and decolonizing mathematics for Indians, ironically, who founded zero and founded arithmetic. But the way that it's made it back to India because of colonization is a very diluted version of zero. So there's his URL for his website. Some fascinating stuff he does, but really he's the one who's inspired me to think about zero. It's one of my latest rabbit hole I fell down. And let me show you what I mean by that. So one of the ways which he uses zero is the idea that he came up with this sort of Brahmaguptan plane, so kind of modeling the Cartesian plane. And what I like about it, it's not just the area model, but it's the area model showing the idea of what, positive and negative, etc. mean. So if you go along the y-axis, that means just sort of the accruement of, the positive of getting something, and down here means the negative. But on the x-axis, you have, let's say, positive to gain fortune, to gain something. And then the negative part of the x-axis is debt. So here it's going to be negative because you are having debt, and the positive means you're having debt added to you, this multiplier of debt. And down here in what quadrant 3, and this is where kids will also be familiar when they get into trigonometry and even just graphing, this third quadrant, you are reducing the debt. So the two negatives will multiply to be a positive, and then right here on the right-hand side, you can see all these simple examples of when you multiply it out, where these values come and how they're kind of interrelated in terms of debt, fortune, and positive and negative taken away. So this was some of the ideas of what Brahmagupta meant in terms of having zero as a locus. If you teach science, electron and proton, electron is a -1, proton's +1. Is electron really less than a proton? Most of the time, negative is seen as in terms of it's like a balancing force. And we have taken negative to mean less. And for zero is meant to be the actually lowest number, and everything was to sort of add to zero in terms of negative and positive. So it's very interesting in terms of what I just came across recently, and that's why I want to include in this presentation here. I would definitely be remiss if I did not mention this book. This is probably the best companion for building a lifetime curiosity for mathematics. It's James Tanton's, and it's self-published, so I apologize for the screenshot of it. But it's called Thinking Mathematics Volume 1, Arithmetic Gateway to All. And when I first got this book, I was a high school teacher. I kid you not. I just bought it as sort of, okay, let me buy one of James Tanton's books. It's arithmetic. I know all of it already. The first 20 pages, I would say at least half the information I'd never come across. And it starts off just by counting, just counting, like the rudimentary ideas of counting, but very quickly goes deeper into ideas of counting, and then of course arithmetic. And that's why this book, to me, is probably the strongest companion for what I am going to be talking about here tonight. What I'd like you to do, normally I do not like to put slides which contain a lot of words. It's one of those sort of things you do not do, especially if we're going to talk over it. So I'm not going to talk over it. But what I'd like you to do is just read this cryptic conversation between two people. One of them is false, is not a real person, but PDT is a real person. And I don't want to sort of unveil his identity just yet, but I'd like you to read this conversation and take a couple minutes, if you will, right now. So the key middle, like it's if you were to look at one word and it just fits perfectly in the middle, most of you would see alienation in that short sentence. Alienation occurs before anxiety, as sort of alluded to in this short, and it's part of a longer conversation. And because I taught occasionally English a couple of times as well, English curriculum is constructed by choosing the books first, and then the curriculum is written around those books. In mathematics, the exact opposite. We write the curriculum first, and then we find books to support it. And what PDT, which I won't give away who he is just yet, is saying is we have to find the best quote unquote books for mathematics, the best problems, the best ideas, the kind of the poems, so we maybe have less of this alienation. He cites that as one of the problems. So who is PDT? He's Peter Taylor. I'm very fortunate to say he's a friend of mine. He's still teaching at Queen's University. I think he's in his 80s now, but he won the Adrien Pouliot Award in 2006 for making significant contributions to mathematics education in Canada. And the key thing is he found was the idea of teaching mathematics as an aesthetic, as an art, as poetry. And that's why he teaches across so many disciplines at Queen's University. He also teaches a course, poetry and mathematics. So again, this idea of really cultivating the best problems in math and showcasing them as pillars to build our curriculum around. And this is his quote. It's actually part of an article, and this is where we can have the rabbit pop in again. Mathematics is about wonder, creativity, and fun. So let's teach it that way. It seems like a throwaway sentence, but why aren't we teaching away the way that mathematics is? So, that's a question for all of us to sort of think about. So this whole chasing rabbits turned into a professional development day at the Museum of Mathematics on November the 4th. And just much like the people in this room, we had a cross section of elementary, middle, high school teachers. I think we had 65 people in a room spending the whole day just doing arithmetic. And it was great because the elementary people, it's like, yes, arithmetic is important. Middle and high school, they see it as foundational piece for their, the higher, more complex thinking and geometry and algebra courses. So it just turned out to be a really wonderful day. So a lot of the ideas which I'm going to share with you tonight are actually coming from this PD that we did, my co-author Chris Brunell and myself in New York. And I'm going to start off with a kind of a quirky problem, but I share this one because this is the one I use for family math nights. when you're really trying to reach the community of parents and anyone else in terms of, having more fun with mathematics and really communicating that sort of curiosity, wonder, and awe that Peter Taylor talked about. So for takeaway one, I know it's like, what's going on here? The answer is 3. Yeah, and that's why I sort of say tongue in cheek, 99% of the time. I say it's mostly 3, but there's a quirky time where the answer is equal to 5. And okay, so the reason why I do this question is because you now have a captive audience. Nobody wants to leave the room. Everybody's interested in how can 4 take away 1 equal 5, no double negatives, actually the physical removal of a object, and you will be left with 5 of those objects. Seems completely crazy, and then I tell them that I'm actually giving you the clue in terms of the piece of paper I'm holding, and eventually people start going, okay, there's 4 sides, there's 4 corners, and then someone has an aha moment that if you cut away one of the corners, you're left with 5 corners. So this is my icebreaker. It's kind of a dad joke in many ways, a dad math joke, but it's the idea of really always having this sort of circumspect sort of eye on mathematics that always sort of look deeper. Maybe there's a quirk. Maybe I can get a different answer by asking a different question. So this is more symbolic for me in terms of as we progress through idea of mathematics. I shared this image on social media, and you can tell by just even, I think it was in a course of maybe a couple of days, it got 407 likes in terms of the staircase model of mathematics. We have this linear progression. And even if you get to the top, what does that mean? And we know that the way that we learn anything is more like this Escher model, this Escher print, that these staircases go all over the place, that someone might take you to this other place that may reconnect you to this other staircase. That's how mathematics evolved. That's its natural narrative. And maybe kids need to explore mathematics in such a way. Visual learners, linguistic learners, kids who are maybe like sort of tactile, manipulative type problems, pencil and paper. Everyone should be able to go down their own kind of roads and through this sort of portal of arithmetic. And sort of related to that, I put these 5 points, and these are 5 criteria for play. It's in the book Math Recess. But the first bullet point, I would say even I was guilty of not adhering to. Is the mathematics that students encounter, is it self-chosen, self-directed? Is there at least one point, let's say, for example, during the week, where kids get to pick their own problems to work on? Can they work by themselves? Can they work in pairs? Can they work in groups? That's the idea of play. So if we're not adhering to that or trying to, then we can't say we're having playful mathematics, because that is by definition the first rule of thumb for play. It's got to be self-chosen, self-directed. I think we're doing a pretty good job of some of the other ones: element of imagination, alert frame of mind, rules and structure. Maybe not this one. That there's always the idea of testing and stuff. Like that's why we're learning it, and maybe not in the moment itself and the appreciative part of that. So that's something maybe we have to work on. But definitely number one, I think, is something that we really have to pay attention to if we're going to adopt play in mathematics. So this past summer was my first kind of official foray into presenting arithmetic in sort of a larger forum. And there was something called the World's Most Interesting Mathematician competition. It was tongue in cheek. They invited 60 mathematicians from all around the world to present their most interesting and fascinating ideas about mathematics. And I lost eventually to Dr. Sophie Carr. It was kind of like a World Cup soccer format where, you have a group stage and then people leave the group stage. And I lost in my first round match to Sophie Carr. And you're thinking, wow, okay, what does this have to do with arithmetic? Well, this is how I lost. Dr. Sophie Carr, who's an aeronautical engineer, she wanted to present the Bernoullis Principle, which is really cool. As a physics teacher myself, that's such a cool, fun principle to present. And she was up against goofy student mistakes. Literally, that's what I chose when I said, okay, I'm going to be on the sort of the social media world stage. I knew I was going to lose with this, but I wanted to give arithmetic a platform. And you're thinking, well, what else could there be here? Okay, fine, that's sort of a fluke. 64 divided by 16 is 4. If you slash out the sixes. What about 95 divided by 19? 95 divided by 19 is 5. If you cross out the nines, you get 5 as well. Are you curious now? You think that's the only two-digit example? There's actually 4 two-digit examples of those student mistakes. And if I was to ask you to find the other two, and I said go, I would be surprised if anybody gave me back the answer within an hour or so by brute force. It's almost impossible. And what you have to do to actually get the other two answers is, ironically, right beside me is algebra. And so this is this simple idea of these sort of innocent mistakes can actually have this bounty of algebra connection by looking at it in a more general scope. And but that was my presentation. But I was so proud that I actually went up against Sophie Carr. This is a game called Albert's Insomnia. I think some of you might have seen it. I've heard about it on social media. And I will talk about it, but there's specifically these 4 cards. So it's a game where you use your basic math operations, and one of the ways you can play it is that you take turns constructing the numbers 1, 2, 3, 4, 5, 6, as far as you can go with PEDMAS operations. If your number is there, you get to point to it. So how would you create 1? 4 take away 3 is 1. How would you create 2? 12 take away 7 is 5. 5 take away 3 is 2. 3 is right there. 4 is right there. So you keep playing until somebody gets stuck and can't produce an answer. And you have your basic operations. But something really magical happened with these 4 cards. I'm going to ask you a question. How would you make the number 120? How would you make the number 120 with these cards? And I can see the actual chat box. I'm scrolling down. So if someone's got an answer for 120 with these cards, just type it in. So the numbers are 3, 4, 7, and 12. Yeah, so Zinli said 7 plus 3, and Tony as well. 7 plus 3 is 10, times 12 is 120. Excellent. But I'm going to ask you the same question, but you can only use 2 cards. Can you make 120? Can you make 120 with just 2 cards? Now you're thinking, right? So I played this, we dealt out these cards, myself, my 2 kids are ages 11 and 13 now, and we got up to 137. There's no way you can get up to 137 unless you introduce more operations. And so the idea is that we introduced exponents, factorials, square roots. And so if I just go back to what I just said, factorial, if you can make 5 factorial from 12 take away 7, it's 5. 5 factorial is 120. There is your 2 cards to make 120. So that was part of the interesting part of these 4 cards. But what also happened was, and this is my son made this observation, when we got to 120, and he said it's 12 take away 7 is 5 and 5 factorial is 120, this is the observation he made. You see, all the numbers from 110 to 119 can be gotten with just the other 2 cards which are left, 3 and 4. So what he observed was the numbers 121 to 129 can be built with this symmetry by adding these numbers. And this was completely by fluke of dealing these 4 cards out. Sorry, Waiting for us way at 120 was this observation about symmetry of the operations and having this 120 be a home-based number. And this is what I loved about this game, that you can go down so many different rabbit holes depending on what cards you get. So you can see all the results from 110 to 119, and I've shown you in terms of the notation. This is another activity I do at Family Math Nights. It's quite simple, and it's a lot of fun. So I want you to do it kind of too, maybe, is I give everybody 2 loaves of bread, and I ask them to share it among 3 people. And this is the most common answer I get back, visually speaking, from parents and kids. Everyone got the same amount of bread. They did. Look at it. Everybody got the same amount of bread. But you notice that one of the breads is broken in half? And this is important. You can't glue your bread back together. What if you had 9 loaves of bread and 10 people? How much bread does everybody get? Yeah, the correct answer is 9/10. But do we ever think about what the bread looks like? 9 people got whole loaves of bread, and the 10th person got a bag full of shards. So maybe that's not equitable. So the answer I show, and this becomes the rabbit hole into Egyptian fractions, unit fractions, is that we still have our answer of 2/3, 1/6 plus a half. So this simple question, which has low floor, everyone can get the right answer, creates discussion about what is a unit fraction, creates the idea of going back to history, Egyptian fractions. And I've had so many parents, look up what Egyptian fractions are because they've never heard of them themselves. So I use this activity to get into the Egyptian fractions and unit fractions. What is the relationship between 19 and 100? You're thinking, is there one? Because that is like the weirdest kind of 19, 100, 19, odd. It's prime too. But what's the first thing that comes to your mind when you think of 100? First thing, type it in. First thing that comes to mind when you hear 100. What are you thinking of in terms of anything? 100. One bigger than 99. Yes, Lee. One of the things that a lot of people say, sort of intuitively, I'm going to type it in, is 10 times 10. 10 times 10 is 100. What's the relationship between 19 and 100 then? If you add the first consecutive odd numbers from 1 to 19, you get 100. And, I used to do this activity when I did elementary classes, just turning those unifix cubes into L shapes in front of kids and telling all kids that every single odd number is L-shaped except the number 1. And then if you start inserting these L's together, you get square numbers. That's as a young kid, that's pretty mind-blowing, especially put the colors in too. So that's why I got the slide right beside it. How do you want to know your math facts? By boring memorization, or do you want to go down that sort of rabbit hole of number theory? The magic of a square. So what I've done is I've made a square, a literal square with the consecutive odd numbers from 1 to 17. Can someone type in what the diagonals add up to? What does the diagonals add up to in this square? Yes, 27. Okay, bookmark that answer. Bookmark it. Let's do it again. This time you get 64. 27, 64. If you take the cube roots of 27 and 64, it gives you 2 and 3 respectively, and that's the length of the side of the square. And I will leave it to you to figure out how that relationship works, because it's really cool. If you take the cube or the diagonal, you actually get the length of the side of the square. that you constructed with these consecutive odd numbers. And that's what I'm saying is we take such an inert look at numbers. We don't play with them. We don't look for other patterns other than ones maybe we were told to look for. So this is something I just came across about a couple months ago. I think it has Islamic origins in terms of this perfect square, perfect cube idea. The next number in this sequence, 164. Can someone type in what the next number in the sequence is? I'm actually giving it away, but there's something else happening here besides the number. But just play along. Tell me what the next number is. And Tony is falling down the rabbit hole. That's good. Keep falling. We'll get you back up a bit later. The next number in this sequence, 729. Thank you, Lee. So I do this for such a roundabout reason. So 729 is 3 to the exponent 6. Well, 164 and 729 are the only numbers under 1,000 that you can take the square root of and the cube root of. And I prove this by using the exponent laws of the exponent 6, because 6 is 2 times 3 or 3 times 2, and you can make it either, 2 cubed becomes 8, 8 squared is 64, or you can go 2 squared, which is 4, and cubed is 64. So I use this example to teach exponent laws. Instead of having a dry exponent law and then doing examples, how about you come out to the back door, do some weird patterning question, show that there's a cool fact about cubes and squares, and then prove it in terms of the exponent law. So again, it goes back to the Escher model of the staircase. We don't always have to approach problems from an A to B to C order, maybe be more Willy Wonka-like, come slantways sometimes too, right? So that's my exponent question. But here's the first rabbit hole we all missed. We all missed this rabbit hole. Every one of us, including myself. If I Google the numbers 1 to 10, this is what I get. You probably get something similar. You get the googly eyes with some of the numbers and, the array, but it's always the same. There's something missing. I never Google 1 to 10 and get this. And you're thinking, well, Sunil, what else would you want to get numbers 1 to 10? If you're typing in 1 to 10 in your Google search, what would you expect to get? I expect to get this. Well, hope. If I was to ask you to add the numbers up 1 to 10, and because it's the PDF, it's not usually some of these lines are hidden, so the whole thing is here. If you flip around the last row and make it 10, 9, 8, 7, 6, you now get 5 columns of 11. So this comes like a mini Gauss story, how Gauss sort of preoccupied his time by adding numbers 1 to 100, and he realized there was 50 101s, and he multiplied 50 times 101. Well, we can create these mini Gausses early. We can just say, hey, add the numbers 1 to 10, and maybe the first mathematical multiplication fact kids know is 5 times 11 after 2 times 2. This is a perfect situation to illustrate what should I do with these 11s, because I have 5 of them. And they came out from a natural aha wow moment. The kids in the sea, you surf their energy and curiosity, and now you can build in the idea of multiplication because you got the 5 11s. Yes, we're on page 26. So here is a question. I actually have 8 steps. I actually found a picture. I think it's 8 steps. So my question to you is, how many different ways to get up these 8 steps? And what I mean by that is you're allowed to take 1 step or 2 steps. So you could go 1, 1, 1, 1, 1, 1, 1, 1, 1, or you could go 1, 1, 1, 1, 1, 1, and a 2 at the end. Because remember, it's always going to be a total of 8 steps. Or you can take 4 hops of 2. So my question is, how many different ways are there to get up these 8 steps? And again, yeah, you can start off and list them all. That's fine. But one of the strategies we like to teach our children, our students, is always start with a simpler case. 1 step, then 2 steps, then 3 steps, So I'm not going to go to the next slide because it's going to show everything. I just want to talk about it. When there's one step, there's only one way. You take one step. When there's two steps, oh, you can go 1, 1, or you can do a hop of 2. So there's two different ways. With 3 steps, you could go 1, 1, 1, 1, 2, or 2, 1. You're thinking 3. It's not very interesting yet, is it? So I'm going to go to the next slide and show you all the results. So at 4, there's 5. At 5, and I've shown the different combinations, there's 8. And you're thinking, I've seen those numbers before. What kind of numbers are those? 1, 2, 3, 5, 8. Somebody want to type it in? Fibonacci. Now, remember, we're chasing rabbits, right? So the rabbit's not going to lead us to Fibonacci. The rabbit's going to lead us to Pingala, the Sanskrit poet, who asked this question of himself 800 years earlier: how many different ways can I write a poem with long and short syllables? Long meaning 2 spaces, short meaning 1 space. So it was actually Pingala, some say Hemachandra, around the same time, who actually founded the idea of these kind of numbers. He actually found the binary system too. So this is the idea: when you sometimes chase rabbits, you tend to get to the real sort of historical true reference of where things came from. So Fibonacci, that's what we know it as, and the rabbits. But if you take it back further, its origins are in Sanskrit poetry, about 300 AD in India. This number is so important that I just left it on its own, too. There's so many great ideas with 2. We sometimes just skip to 10, base 10, but I think base 2 is really cool. So one of the participants that's here tonight, is May still here? May Volz, I went into her class in Coppell, Texas, just this past year. And I was in a 5th grade class. And so I've done some of these problems with her class. So some of these have been beta tested in terms of having fun with them. And there's May. So this is one of my favorites, is that you ask kids to, or whoever, to find their birth date. So if their birth date's 22, try to find as many cards they found 22 on. And if they just point to the cards to me, I can tell them their birth date. So, if someone says, okay, my birthday's on card 310, I can tell you your birth date. So what I'm going to do is I want someone to play along. I want someone to type in what cards they found their birth date on. Now, it can be on one card, it can be all the cards, but please double check that you found your birth date, not the month, on all the cards. So if somebody wants to type in what cards they found their birth date on, I will tell you what birthday, your birth date. Cards 2 and 1 for Rana. So Rana was born on the 6th. Anybody else? I'll tell you a couple more. Cards 3, 4, 2. So yeah, that's Sandra. So Sandra, you were born on the 28th. Xin Li was born on all the cards except card number 3. So she was born the 23rd. So I'm just going to go to the next slide because on social media, Margie Pierce, a kindred spirit, she forgot I'd shared this on social media, so she forgot it. And so I'm going to give you the clue. Lisa says all the cards, so she's born on the 31st. Christine says cards 2 and 4, so she's born on the 20th. So the key thing is the top left-hand corner numbers, the binary numbers. So the only way to make, for example, my birthday, 27, is cards to use a 16 plus an 8 plus a 2 plus a 1. On, off, on. And what I have, I don't just photocopy these cards. I have kids make the cards. So they write 1 equals 1, 2 equals 2, 3 equals 1 plus 2, 4 equals 4, 5 equals 4 plus 1. I make them write down all the binary additions from 1 to 31 and then group them in terms of where they would have all these. So the kids make their cards. And that makes it more fun because they understand the binary. So this is the base 2 mind reading trick. Here we have Lucius. And this is how the book Math Recess started with this student. And so he was such a remarkable kid. And he came up and was playing this game called the 50 game. And this is how the book starts. And I will explain the 50 game and we'll kind of play along. So what the 50 game is, I would write the number 50 on the board. And what we would do is we would take turns removing a number from this 50 until we got to 1. And when there's whoever turn is when there's 1 left is the loser. But there's a key thing. You can never take more than half. So if Lucius went first and he took away 49 from 50, the number would be 1. It'd be my turn. It's 1. I lost. It doesn't work like that. You can never take more than half. So if you start with 50, you can take up to 25. You can take 17, 19, 2. Can't take 0. You always got to take something away. So we played this game over and over, and the kids were always losing. And then Lucius was like the 7th person who tried to, vanquish all the losses. He was like the contestant of Price is Right. The kids were cheering at the next move. They couldn't figure it out. So really, this game has this sort of nice 2n to the exponent n minus 1 sort of patterning. These are the danger numbers. So if we started at 50 and I went first, I would take away 19. You're on 31. You cannot get me down to the next danger number, which is 15. The most you can take away is 15 and to 16, and I would take away 1 and be 15. So these are the danger numbers. So I can play this game till whenever, as long as I know the pattern. So again, this idea of a game base 2 and 2n to the minus 1, we've seen that also in Tower of Hanoi. If you know familiar with the Tower of Hanoi problem, if you got 3 discs, and how can you put another peg without one having a larger one on top of a smaller one having the same orientation? With 3 pegs, it takes 7 moves. That's 2 to exponent 3, take away 1. So again, that base 2 is a really important idea to introduce to kids, either through games or through these kind of puzzles like the Tower of Hanoi. And that's why I put 2 to the n minus 1. And for me, the most important 2 to the n minus 1, and I got my daughter's handwriting coming up, that number there, that is the largest Mersenne prime found now. I think the 51st. It was found in December 2019. And this is a true story. It's in the book. It came across my news feed. My daughter came home from school. She was having some snacks, watching Fuller House, had her headphones on, and she was in 5th grade at the time. And so I asked her, Rhea, 2018, Rhea, do you want to know something cool about primes? She said, yes. I said, they just found the largest prime number, because my daughter loves primes, but she doesn't know anything about exponents. But this gave me an opportunity to talk about exponents. It didn't have to wait till middle or high school. I then said, see, Rhea, you see this large number? Can you read it for me? And she read it, 82,580,933. That's a number of times you have to multiply 2 by itself. She took out her school calculator and started punching in 2 times 2 times 2 until the 13th time it said overflow on her school calculator. And then I calculated dinner time. I didn't do this right away. I couldn't figure it out. But I told my daughter it would take you 8 months of tapping, even if a computer screen was big enough, to generate this prime number. And so, again, we capture the imagination, curiosity of kids by sometimes larger ideas coming further down and just within their reach so that they can be really excited about it. So this is when I taught my daughter Mersenne primes, but more importantly, the idea of what exponent is. May will recognize this question. I did this exact question in a 5th grade class in Coppell, Texas. I kind of made up this question I didn't make up the question, but I made up I decided to do this question in a fifth grade class because it's actually a high school question. And it's not a high school question yet. So I asked them, are these numbers divisible by 5? And I wrote the fourth one. And the kids are bored. They're yawning, going, please just finish writing the whole number because they just look at the last digit. And then I said, okay, I got one more for you. I got 173 plus 97. And they, again, half of them said, we just had 7 and 3. And so I purposely put myself as almost looking like some sort of like Shakespearean fool character, like, oh no, I got one more for you. And they're laughing at me. I've disarmed these fifth grade students. They're like loosey goosey. I go, okay, give me one more chance for divisibly by 5. This one's going to stump you, I promise. And they're so confident and they're curious because I'm giving a long pause. And I go, you have to add 2 numbers for me. And they go, yeah, we did that. It's easy. See, that's the one I give them. 3 to the exponent 444 plus 4 to the exponent 333. Now they have to know, what does this number even mean? Now they are curious as to how to unpack it. So some of the students had actually known exponents, but you can't do this question on a calculator. It won't fit. So we have to get into the idea of unpacking and looking for patterns, looking for repeating patterns, and basically indirectly talking about modular mathematics. So I apologize for these numbers not being in superscript, but you can see that the base 3 is going to oscillate between 3971, 3971, 3971. And base 4 is going to just toggle back and forth between 4 and 6. And every fourth one for base 3 is going to end up in a 1. And because 333 is an odd exponent, it's going to be 4. And now we can figure out that this number is divisible by 5. This is a high school math contest question, which I came back a backdoor method. Accessibility of, okay, what I can do with these kids. Curious to go, okay, give me one more. And now they got the energy to go, you know what? Okay, tell me more about this number. If I give this question to high school kids, it's kind of dry. Okay, I can solve it. But again, so much curiosity, an everlasting curiosity can be created if we take some of these ideas further down into middle and elementary. I'm not going to play this. This is actually, speaking of base 4, I did this in Bridges Festival, Waterloo, Canada, with 1,024 pieces of Lego. And I built this level 5 Sierpinski pyramid with Lego. This whole idea, and this is where, again, I talk about exponents, 1,024. There's different representation of 1,024. 2 to the exponent 10, 4 to the exponent 5, 32 squared. They all mean 1,024. But 4 to the exponent 5, if you keep making these kernels, these nuggets of the base 4 pyramid, you keep reiterating that 5 times, 5 levels, you get this fractal. So I'm going to just skip the video of that. It's kind of cool. Okay, so the last thing I want to talk about, well, one of the last things I'm going to the end, this to me is the greatest K-12 math problem ever. Okay, I'm kind of somewhat exaggerating, but I do think it is cool because every level of student has access to this question and access to their mathematical maturity. So what you have to do is you have to put the numbers 1 to 9 into the slots A, B, C, D, X, Y, W, X, Y, Z. I almost forgot my alphabet at 10 o'clock, just 10 past 10 Eastern time. The capital letters and the ones in circle represent cows. And the bridges with the lowercase letters, they represent the sum of adjacent fields of cows. So if A was 1, B was 2, X is 3. That's pretty easy. But you can only use each number once. Now, what I like about this puzzle is there was actually a teacher, instead of using pencil and paper, used Unifix cubes and had Unifix cubes of towers of 1, 2, 3, 4, 5, 6, 7, 8, 9. And so kids could quickly move around these towers instead of scribbling and starting new pieces of paper. It was also saving paper. So it was really fast to move around these pieces. So even grade 1 kids can try with trial and error single digit addition. And maybe the higher elementary kids can start thinking about what numbers can the fields and bridges not be? Can a bridge be 2? Because the only numbers that add to 2 are 0 and 2 and 1 and 1. You can't have 0 cows in the field. There must be a number. You can have 1, but you can't use 1 twice, so the bridge can never be 2. So kids start thinking like that. And maybe in higher uh, middle school, early high school, kids can think about even and odds. Just label the whole bridge and field system with E's and O's. Is it possible to have solutions with E's and O's to give you some insight as to what the numbers are? And finally, for high school kids, this is an algebraic solution. So right away in first, second grade, kids are exposed to 8 variables. So they're not as intimidated if they see algebra later on. So for me, algebra is more like the circulatory system in mathematics. It's not an appendage. It's not a course waiting for them in high school. Algebraic thinking can occur far earlier on and have far lasting benefits if it is sort of thought about early on. This is a square adding problem. I love this problem. What you have to do is numbers 1 to 16. And what you have to do is you pick any number, and the number you write after it, and again, you can only use each number once, so all the numbers 1 to 16 have to be used. So let's say if I pick 9. The next number I have to put beside 9 has to be 9 plus something gives you a square number. So if I write 7 beside it, 9 plus 7 is 16. So I can't use 9 and 7 anymore. Now I'm at 7. What can I add to 7 so it gives me a square number? If I write 2, 7 plus 2 is 9. So now I have a string so far that reads 9, 7, 2. What could you add to 2? Well, I could add 14. 2 plus 14 is 16. You can repeat the square numbers, but you can't repeat the numbers in the string. Can you create and use all the numbers to create this square adding problem? It actually becomes a really rich graph theory problem. It doesn't matter where you start. You can actually create these chains together. And there's a great video for it on Numberphile. When I should have included the link for it. So again, a really fun problem with not a lot of big numbers in the hundreds and things. 1 to 16, idea of what a square number is, really building those math facts of what a square number is. 9, 16, 25, those are the ones. And it's a challenge. It's a good challenge. So I really like this problem, and it's one which I just sort of came across myself the last couple of months. That's why it's like the second last slide. And the last thing I'd like to leave you with, this is not for 2021, 2021, it's a long ways away. But I have started writing the book for Chasing Rabbits. It'll be out in the fall of 2021. And these are the tentative chapter titles. Very cryptic in terms, especially the first one, Ready, Set, Stop. And we won't really go to the 8th chapter. So some of these ideas you will see in the book, but they'll be interwoven with some larger, more macro ideas about really what is mathematics and what is the purpose. And so there we go. Chasing Rabbits, hopefully building a lifetime curiosity for mathematics through arithmetic for not just your students, but yourselves as well. Thank you so much.
Thank you, Sunil, for your presentation and your patience with technology today. Are you able to hang out for a few more minutes for any questions?
Absolutely.
Sunil, there's a couple questions in the chat window that you maybe want to address verbally rather than typing in the chat window.
Yeah.
Specifically, Farquin has the question about how can I spread this to my elementary colleagues who don't have a love or background in math that I do?
That's a really good question. And I use the elementary, I mean, both my kids have elementary teachers, and elementary teachers do so much. I mean, they teach 5, 6 different subjects, and they wear so many different hats, and a lot of them don't have a math background, and they feel they're not math people, and they don't want to give as much time to math, and they have their own math anxieties and phobias, which is very. So I would first start with, before the loving it, is to give teachers the space to talk about their anxieties, um, and to be free, and to affirm that these anxieties are quite normal. And it was built in terms of just maybe the way that they experience math. And I think it's really important to listen to these teachers first, and to really let them air out their any anxieties and misconceptions they might have about math. Even if, like, I'm just teaching, it's part of my job, I'm not a math person. Really have that conversation first, and then once you have let them do that, you build a trust level. Then I think you can start with the, well, maybe here are some things for you to embrace or love mathematics. But I really think elementary teachers are so important, and we need to support them. And I think the best way to support them is to first listen to them. There.
Are there any other questions for Sunil?
Thank you, everyone.